Hey folks, and welcome to Unit 6. Unit 6 is going to go pretty quickly, and we're going to cover a lot of ground. We have kind of four distinct topics. First one is rotational energy. Second one is angular momentum. Third one is rolling motion. And fourth one is orbital motion. The only one that is totally new to us is going to be angular momentum. Everything else is just going to be an extension of something that we already know about. So we'll get started with rotational work and energy. Because this is about energy, there's some stuff that I'm going to gloss over that I want you to make sure you review from like Unit 3, because all the things that we talk about are going to be the same, just we're talking about rotation. So we'll start off quick. If a net force is applied to an object for a certain displacement, those two variables happening talk about work being done. So work has been done. In Unit 3, we learned about work being the product of the force and displacement, but specifically the component of the force that is parallel to the displacement. We also briefly talked about how a graph of force versus position can be used to calculate the work. If there is a variable force or a constant force that happens over the course of the displacement of an object, and you found the area underneath or between that line and the x-axis, that area is equal to the work that has been done. So that's something that I'm going to gloss over. You can review on your own. If work has been done by the net force, then we say that kinetic energy has changed. That's only if the net force has done work, and for the most part in rotation, that's the situation that will happen. And so work done by the net force results in a change in kinetic energy. Kinetic energy is 1/2 mv squared, so a difference between final and initial. Okay. Same thing can be said of rotation. So if a net torque is applied for a certain angular displacement, so imagine I take a bike wheel and I grip it and I turn it a certain amount and then let it go. The torque that I applied times the displacement of the wheel while I was causing the torque is going to also result in work being done. So if the net torque is applied over a certain angular displacement, then we can say that rotational work has been done. And so, translational work is force times displacement. Rotational work is just the analogs for those variables. So rotational work is going to be torque times angular displacement, so tau theta. And so the same relationship exists. I'm not going to draw the full picture here, but if you had a graph of torque versus angular displacement, then you could analyze that graph and find the rotational work that has been done. The other result in a net torque being applied for an angular displacement is that the rotational kinetic energy has changed. So what rotational kinetic energy is, there's a derivation in your textbook, but I'm going to summarize it here. Rotational kinetic energy represents the energy of all particles in a system as they travel a circular path around a common axis. So basically, every particle that's moving in a rotating object has translational kinetic energy, the 1/2 mv squared, because every object moves in a straight line over a short distance. If you add up all of that translational kinetic energy, you get the rotational kinetic energy, because every particle has its own rotational inertia, and every particle also has its own angular velocity, or the common angular velocity. So in total, the kinetic energy for rotation is 1/2 the rotational inertia times the angular velocity squared. Now, when you do rotational inertia, that's the part that you get when you add the rotational inertia of individual particles. You get the overall rotational inertia, and that is in joules. So the last thing that I want to talk about is I've just used the words translational and rotational. I want to make sure that they're clear. Translational kinetic energy is 1/2 mv squared. You can use a T subscript if you want. I would only use that if you know there's also going to be rotation involved. That energy exists if the center of mass moves. So to translate means to move from one place to another. So if the object is at one point in one instant and then a different place at a different instant, then there must have been translational kinetic energy to bring it there. Rotational kinetic energy, 1/2 iota omega squared. You can put an R or ROT subscript there to show rotation. You'll see that in some problems that you do, I bet. That happens if the system rotates about an axis. And so, technically everything is 1/2 mv squared, but if we add up the energy of every particle that's rotating, we also get rotational kinetic energy. So the translational is the sum of all the center of mass velocity, and then the rotational is the sum of all the rotational inertia and the rotational energy there. The last thing I'll leave you with here is just the idea that these two types of kinetic energy can exist in 3 possible combinations. You can have both of them at the same time. If you throw a football or a baseball or a boomerang or a frisbee, they will all rotate and translate at the same time. You can have either one of them but not the other. So if you dropped a textbook, it would gain translational kinetic energy. If you that bike wheel I was talking about, if I just held it in front of you and spun it, then it would have rotational but not translational. And then obviously objects at rest can have neither type of energy. So that's 4 combinations. And that's what I'll leave you with. Thanks.